And again, these are just examples to bolster our theory. In the next lesson, we're going to do a lot more examples. So evaluate the following limit using L'Hopital's rule. The limit as x approaches 0 of 1 plus sine x raised to the cotan x power. Okay, well, as x approaches 0, sine of x is going to equal, it's going to go to 0. So this is going to equal 1. And as x approaches 0, cotan x goes to infinity. So this is 1 to the infinity power. This definitely qualifies as an indeterminate power. Indeterminate. Okay, well, here our function is y equals 1 plus sine x raised to the cotan x power. When we take the natural logarithm of both sides, we're going to get the natural logarithm of y equals the natural logarithm of this, which is going to equal cotangent of x times the natural logarithm of 1 plus sine x. When I take the limit of this, now when I take x going to 0, I'm going to get infinity times 0. This is an indeterminate product. So far so good. We're working out. How do we deal with an indeterminate product? We drop one of them down into the denominator. So I'm going to write this as ln y equals ln of 1 plus sine x all over 1 over the cotangent of x. Okay? Well, this is nothing more than the ln of 1 plus sine x. 1 over cotan is the tangent of x. When I take the limit as x approaches 0, I'm going to get the logarithm of 1 is 0, and this is going to be 0 over 0. Now that I have an indeterminate form that matches L'Hopital's rule, I can apply L'Hopital's rule. In other words, I'm going to take the derivative of the top, the derivative of the bottom. Okay. The derivative of the top, the derivative of a logarithm is going to end up being, when I take the derivative, I'm going to skip a couple of steps, I hope you don't mind. I'm going to get the cosine of x divided by 1 plus the sine of x. And the derivative of the bottom is going to be secant squared x. Now I'm going to go ahead and take the limit of that as x approaches 0. And I'm going to get 1 over 1 for the top, and I'm going to get 1 for the bottom, which equals 1. And that's my final answer. So the limit, but notice I found the limit of this thing, which is actually the natural logarithm of y. I didn't find the limit of y itself, so I have to take that extra step and bring it back. We ended up taking the natural logarithm to find the limit. So it's the limit as x approaches 0 plus of the natural logarithm of y. That's what equals 1. Now let's go ahead and bring it back to the actual limit itself. So let's just recap. We wanted the limit as x approaches 0 of y. Well, y is equal to e to the ln y. So the limit as x approaches 0 to the plus of y equals the limit as x approaches 0 from the plus e to the ln y, which equals e to the 1, because we found the limit of that, which is equal to e. So there we go. We found our limit. We had a power, we took the logarithm of it. The logarithm gave us a product. We took that product, we turned it into something which is 0 over 0. We applied L'Hopital's rule. We found the limit of the natural logarithm of y because of that first process to simplify it. Now we just reverse it. If you take the logarithm of something, if you want to go back, just exponentiate it. We didn't really need to go through this. It's just going to be e to the 1 power. That's it. So once again, we will continue on with more examples, exclusively examples, applying L'Hopital's rule in the next lesson. Thank you so much for joining us here at Educator.com. We'll see you next time. Bye-bye.